Hello everyone, and welcome to UNISEC Global's Mission Idea Contest lecture series. As you know, the 7th Mission Idea Contest, MIC7, is seeking your brilliant and innovative ideas towards the advancement of deep space science and exploration. We are very excited to bring you the first lecture by Professor Funase in a series of 5 lectures to assist you with your mission designs should you join the contest. I'd quickly like to just give you some housekeeping rules. If you have questions throughout Professor Funase's presentation, please post them in the chat. We will be allocating time for questions at the end of the presentation. It will run for approximately an hour, and we should have approximately 20 minutes for Q&A. Dr. Funase obtained his PhD from the Department of Aeronautics and Astronautics, University of Tokyo in 2007. And after 5 years of research and development for deep space exploration spacecraft in JAXA, he has been an associate professor at the University of Tokyo since 2012. Since 2019, he also works as a professor for JAXA ISIS, the Institute of Space and Astronautical Science. As a project manager, he successfully launched Procyon, the world's smallest deep space probe weighing 65 kilos in 2014, and is currently leading the development of EQUULEUS, a much smaller 10-kilogram CubeSat that will be launched this year to explore the lunar Lagrange point. Today, his lecture is based on his experience in the research and development of such deep space micro and nano satellite spacecraft. So please join me in welcoming Professor Funase. Professor Funase, you have the floor. Please take it away.
So hello and good evening, everyone. I'm Ryu Funase from the University of Tokyo and also JAXA. So today is the first lecture in the Mission Idea Contest lecture series, and I would like to explain how deep space exploration missions can be realized by micro or nano satellites. In this lecture, I would like to talk about how to think about deep space missions and how to design a spacecraft by referring to examples, actual examples of exploration missions using micro or nano satellites. But before going to my lecture, let me overview my experiences on small satellite development activities at University of Tokyo and JAXA. When I was a graduate student at the University of Tokyo, I was involved in the development and launch of 1 CubeSat and 2 CubeSats. I was very lucky to be involved in the development of the world's first CubeSat named Sci4, which was launched in 2003. And after that, after obtaining doctoral degree and graduating from the University of Tokyo, I started to work for a Japanese space agency, JAXA, and I was involved in not so small but large deep space missions like Hayabusa and Hayabusa 2 and EQUULEUS mission. Then I returned to University of Tokyo as an associate professor in 2012, and since then I have been working on deep space exploration by small satellites. And as a project manager, I initiated the project to develop ultra small deep space probe named Procyon in 2013, and Procyon conducted the 1-year deep space flight while conducting technology demonstration missions and science observation missions. After that, I am currently leading the development of a much smaller 10-kilogram CubeSat named EQUULEUS that will be launched this year to explore the lunar Lagrange point. So in today's lecture, I'd like to explain how to design a deep space probe based on my experiences. So first of all, I would like to talk about deep space exploration missions in general. I would like to give an overview of the types of celestial objects to be explored and the methods of exploration that have been used in past missions. Now let's take a look at the types of celestial objects to be explored. First, there are planets. The planets include Mercury, Venus, Mars, Jupiter, Saturn, and so on. Then there are natural satellites that orbit around the planets. For example, the Earth has a moon, Mars has Phobos, Jupiter has Europa, and Saturn has Titan. Actually, most of the planets have multiple satellites around them. And asteroids and comets are much smaller objects in the solar system. So far, more than 20,000 asteroids and 4,000 comets have been discovered by the ground observation, but only a few of them have been directly explored by deep space probes. Recently, interstellar objects have also become a hot topic. Here, Oumuamua was discovered in 2017, and it flew away from the solar system after once approaching the Earth at high speed. There is a lot of interest in exploring such interstellar objects that have their origin outside of our solar system. But since they stay in our solar system for a very short period of time, I think we need to devise a novel way to explore them with some kind of spacecraft. In considering a deep space exploration mission, we need to learn about the various mission styles. In other words, how we explore the target celestial body. Typical mission styles include flyby missions, rendezvous missions, orbiter missions, landing missions, and sample return missions. In the order of simple missions here to more difficult missions with more complicated and larger spacecraft system. A flyby mission performs a one-time observation of the target when a spacecraft passes the target. Since the spacecraft only passes by the target object, there is no need for a large delta V or orbit control capability by the spacecraft itself. Therefore, this type of mission is suitable for small and lightweight spacecraft missions. ESA's GEOT mission is a famous example of a flyby mission, which was launched in 1985 to explore the Halley Comet. As shown in this image, the spacecraft made one chance snapshot observations while approaching the target at very high speed. The second is a rendezvous mission, in which the spacecraft controls its own orbital velocity until the relative velocity to the target object becomes completely zero, and they stays in the vicinity of the target object for a long period of detailed observations. An example of a rendezvous mission is the NEAR mission launched by NASA in 1996 to explore the asteroid Eros. As shown in this figure, the mission was able to map the entire surface of the asteroid Eros by observing it from various angles over a long period of time. I think this kind of observation is very difficult for flyby mission. Orbiter mission is to put the spacecraft into an orbit around a celestial body such as a planet. This mission style also requires a large delta V, A typical example of an orbital mission is the Galileo mission launched by NASA in 1989, which observed Jupiter and its moons while orbiting around Jupiter. And it also carried a small probe, entry probe, which was deployed into Jupiter to observe the atmosphere of Jupiter. As a landing mission, I would like to mention Mars Pathfinder, which is a Mars landing mission launched by NASA in 1996. Mars Pathfinder operated not only a lander, but also a small rover like this in this picture, and the rover observed the planet in detail. The advantage of landing missions is that they can observe information near the surface of a celestial body in detail for a long time. The most difficult and complicated mission style is the sample return mission, in which the spacecraft flies to the target object, rendezvous with it, lands, collects the surface material, and brings it back to the Earth. This is a difficult mission because it requires a very complex system, especially a highly efficient propulsion system capable of producing a large delta-p. However, once the sample is brought back to the Earth, it is advantageous in that the material can be thoroughly analyzed with the full range of ground-based analytical equipment based on the latest technologies. Other mission styles, such as rendezvous missions, must rely on the analysis technology at the timing of the spacecraft launch, and can only carry the minimum amount of analysis instruments due to the launch mass constraints. These constraints inevitably limit the quality and the quantity of the observation. One of the most famous examples of a sample return mission is Hayabusa, the world's first asteroid sample return mission launched by JAXA in 2003. There are other types of missions, such as NASA's Deep Impact mission. In this mission, a small probe was impacted with a comet at very high speed, and the mother spacecraft here remotely observed the impact phenomenon and the material blown out by the impact, so that the spacecraft can obtain information about the interior of the target body. And recently, the use of nano satellites for exploration mission is also being considered even by national space agencies. For example, in the case of this Comet Interceptor mission, which is to be jointly conducted by ESA and JAXA, and it will observe comets from multiple directions with multiple spacecraft while performing a very high-speed flyby of the comet to make one chance observation fruitful. So, so far, I have talked about deep space exploration missions in general. We have outlined what kinds of celestial objects can be explored and how they can be explored. Now, I would like to introduce some actual examples of deep space exploration missions by nano or micro satellites, which are strongly related to this mission idea contest. First is the Procyon mission, which was the first full-scale deep space exploration mission by a 50-kilogram class microsatellite. It was a joint mission between the University of Tokyo and JAXA. And as you can see, the in-house development activities was carried out mainly by a team of graduate students and staff from the University of Tokyo and JAXA. And it was equipped with a highly efficient ion engine for orbital control. And it aimed at flyby observation of an asteroid using the Earth's gravity assist technique. So Procyon was launched together with Japanese second asteroid sample return mission Hayabusa 2 in 2014. Unfortunately, the spacecraft could not reach the asteroid, but all the basic functions of the microdeep spacecraft were confirmed to work in orbit, and science observation missions other than the asteroid flyby observation were successfully performed, such as the imaging of the Earth's corona or hydrogen atmosphere, and observation of halogen emitted from this very famous Churyumov-Gerasimenko comet here. And after Procyon, my next challenge was to minimize the deep space bus system into the size of a CubeSat. We are currently developing EQUULEUS, a 6U CubeSat that will be the first CubeSat to go to the lunar Lagrange point. This CubeSat is scheduled to be launched this year on the first flight of NASA's Space Launch System launch vehicle. And NASA JPL's Marco spacecraft was the first CubeSat to successfully perform deep space flight to a planet other than the Earth. Marco consists of two 10-kilogram CubeSats, and they successfully performed a flyby of Mars in 2018. Their mission was to relay the telemetry back to the Earth during the Mars landing of the main spacecraft here, and launched together with the Marco spacecraft. And the mission was very successful. And as you can see, the field of activities of micro or nano satellite is gradually expanding from conventional low Earth orbit to deep space environment. So this is the background why the mission idea contest is conducted, focusing on the deep space mission by micro or nano satellite. So up to this point, I've been talking about introductory topics. And from now on, I would like to explain how the conceptual design of a deep space mission is carried out in detail. A system block diagram of a deep space probe looks like this. This is an example of EQUULEUS system block diagram, which is a 6U CubeSat. Here is the power supply system and ADCS or attitude determination and control system, and CDH, command and data handling system. And here is a thermal control system. These subsystems are not so different from the usual or conventional normal Earth orbiting micro or nano satellites. On the other hand, the mission-subsystem and communication system and propulsion system are unique to deep space missions, and they require special considerations. So from next slide, I would like to explain the design flow for the deep space mission, focusing on what is peculiar to the deep space missions. The rough design flow looks like this. First, we decide the target to explore. And after deciding the exploration target and designing the trajectory to the target and calculating the launchable mass, then we conduct the spacecraft system design. which includes the design of mission-subsystem, communication-subsystem, ADCS, attitude determination control system, and power-subsystem, structure-subsystem, and thermal control subsystem. So let us have a look at each step one by one here. The first step is to determine the exploration target. As explained earlier, we should choose which objects to explore from among planets, satellites, asteroids, and so on. Then we need to clarify the reason why we want to explore the object. In other words, we need to clarify what kind of knowledge we are trying to obtain through the mission. For example, in the case of Hayabusa 2 mission, we can say we want to study the origin and evolution of the solar system by exploring the C-type asteroids. I think this step is the most important in the design activities, because if you have a strong personal interest and the motivation here, it will help you accomplish the hard design work that follows from now, and it will definitely improve the quality of your design work. The next step is trajectory design and the launchable mass calculation. You can design a trajectory from the Earth to the target object by solving a problem called the Lambert problem. The procedure is as follows. First, determine the departure time from the Earth and arrival time at the target. Next, calculate the positions of the Earth and the target at each timing. In this process, various databases can be used to calculate the positions of celestial objects. And once the departure and arrival positions of the spacecraft in the sun-centered inertial coordinate system and flight time are provided, the trajectory can be obtained by solving the Lambert problem. You can use free libraries such as PyCap to solve the Lambert problem. If a trajectory obtained by using such kind of software, the velocities of the spacecraft at the time of departure and arrival can be calculated. And the relative velocities with respect to the Earth at departure and relative with respect to the target at arrival can be calculated by taking the difference between the velocity vectors of the spacecraft and each celestial bodies at each timing. Then you can search for optimal Earth departure timing and target arrival timing that minimize the relative velocities. And if you need reduce delta V more than that, consider using the gravity assist techniques. You can refer to this paper, for example, for more details on the idea of gravity assist techniques. And once you know the orbit, especially the conditions for departure from the Earth, you can estimate the launchable mass. Here, C3 is the square of the relative velocity of the spacecraft to the Earth at the time of departure. And the mission idea contest document provides a graph here that shows the relationship between C3 and the launchable mass. So you can calculate from this figure the launchable mass. So the next step is to estimate the delta V to put the spacecraft into the mission orbit. For example, In the case of rendezvous missions, relative velocity to the target needs to be completely canceled out at arrival, and the spacecraft needs to have so much delta V capability. In the case of orbiter mission, the spacecraft enters the gravitational field of the celestial body in a hyperbolic orbit and be injected into the circulating orbit by performing large delta V at its periapsis. In other words, at the closest point to the celestial body. So in this case, we need also a large delta to put the spacecraft into the mission orbit. In the case of flyby mission, once the spacecraft enters the trajectory to hit the target, it only needs a small amount of delta V to adjust the trajectory. So in this case, we do not need a large amount of delta V to put the spacecraft into the mission orbit. And based on the launchable mass and the magnitude of the delta V in deep space, you can calculate the remaining mass, not including propellant, that can be delivered to the target model. For this calculation, the very famous Tsiolkovsky equation can be used, where you can calculate the final remaining mass, MF, from the propulsion system performance, ISP, specific impulse of propulsion system, and the required delta V here, and the total mass at launch, MI. So please note that this result or this equation is strongly influenced by the performance of the propulsion system. So you need to, so the selection of the propulsion system is very important in the design of the deep space mission. And at this moment, if the resultant residual mass becomes too small and the intended mission will not be achieved with this small mass, then you can go back to step 1 or target selection process so that the required delta V is reasonably small. So at this moment, we need some kind of iteration procedure. And from here, we will move on to the design of the spacecraft itself. The first thing we need to do is to design the mission subsystem. We need to think about what kind of physical quantities we need to measure on the target and what kind of instruments we need to use for that measurement. And you may want to consider or design a completely new instrument for your mission, but I think that would be a very difficult task. So I think it is a good idea to for you to investigate whether there is a similar instrument in the past missions and use it as a reference. So the output of this step 3 includes the very basic parameters such as the size, mass, and power of the onboard instrument, and the field of view requirements for where the instrument should be pointed, and the amount of data to be generated, and the data rate, and the requirements for attitude pointing accuracy and attitude control stability, and so on. The next step, the fourth step, is to design the communication subsystem according to the mission to be performed. So first, we need to organize communication data rate requirements. We should divide the entire mission period into several phases and examine the communication data rate requirements for each phase. For example, we need to consider the following requirements. First, HK housekeeping telemetry, which contains very critical information for the survival of the spacecraft, should always be downlinked at a certain frequency. For example, ProCum mission. In the ProCum mission, the packet size of the HK telemetry is about 500 bytes, and it should be sent at least once every 30 seconds. This is an example. This was an example of a ProCum mission design. And in addition to acquiring HK telemetry in real time, you should also consider to store the HK telemetry during non-visible time at a certain frequency. By downlinking the stored data during the next visible time, we can confirm whether there is any anomaly in the state of the spacecraft during the previous non-visible time. In addition to HK telemetry, we need to consider when and how much mission data or observation data are generated and how long time the spacecraft can spend in transmitting the mission data to the Earth. So based on these calculations, you can determine the communication bitrate requirements for each mission phase. So based on this communication data rate requirement, the communication system should be designed. The key design parameters are the RF output power and the antenna gain of the uplink and downlink lines. These parameters must be designed to satisfy the communication data rate requirement, which in turn determines the size and weight of the power amplifier in the communication system and antenna to be mounted on the spacecraft. So this process will determine the size and the mass of the communication system. So this is a brief overview of the communication system design process. And for more information on the communication system design, please refer to this ProCum paper on deep space communication system design. And this is a specification for NASA's ground station for deep space mission. The next step is to design the ADCS, attitude determination and control system. So actually, most deep space missions require 3-axis attitude control for communication in order to communicate with the Earth and in order to observe the target object steadily. So recently, 3-axis attitude control systems have become common for micro and nano satellites. So this aspect should not be a problem for our mission design. Important difference from Earth orbiting missions is that we cannot manage angular momentum of a satellite using magnetic talkers, because there are almost no usable magnetic fields in deep space. So an external torque source that does not depend on the magnetic talkers is required for deep space missions. And we typically use a propulsion system for this purpose. And similarly, attitude determination using Earth sensors or magnetic sensors is not possible in deep space. Therefore, a 3-axis attitude control system for a deep space mission would typically look like this. For example, sun sensor, star tracker, and gyro are used as attitude sensors. And the reaction wheels and RCS or propulsion system are used as actuators for attitude control. So compared to conventional nanosatellite missions, if there are no mission-specific hard attitude control requirements, then we can assume existing attitude control system for nanosatellites. For CubeSat class spacecraft, we can use the integrated ADCS units and micropropulsion system that are available in the market. For larger spacecraft with a mass of 50 to 100 kilogram weight, we need to use larger reaction wheels that is compatible with the moment of inertia of the spacecraft. And disturbance sources, actual disturbance sources are also unique for deep space missions. The dominant actual disturbance in deep space is solar radiation pressure. If large deployable solar array paddles are employed in the design process, you must care the angular momentum management. Since we do not want to perform frequent angular momentum desaturation operations or unloading operations, we need to consider large reaction wheels with a sufficient margin for the rate of angular momentum accumulation, which will threaten the mass budget of the spacecraft. So there are many things to consider in the design of attitude control system for deep space missions. So the paper on attitude control system design of EQUULEUS here, and the paper on attitude control system design and on orbit operation results of Procyon are shown here as references. So please read these papers for more detailed discussions. The next step is to design the power system. In the design of power supply system for deep space missions, we want to use solar cell paddles, solar array paddles with a large area, because we want to secure enough power at the distance from the sun. However, it is important to note that the complexity of the design varies greatly depending on whether solar cells are body-mounted or deployable paddles. If the power can be provided by body-mounted solar cells, the subsequent spacecraft design process becomes often easier in most cases. Therefore, it is a good idea to examine whether body-mounted solar cells are feasible or not at the first time. However, relying on body-mounted solar cells is not always a good thing, because it has the drawback that the outer surface of the spacecraft is covered by solar cells, and this fact reduces the flexibilities of the thermal design activity. So, and on the other hand, if a deployable solar array paddle is required, the complexity of the spacecraft design will increase drastically. For example, it is necessary to design a complex onboard component layout to meet various operational requirements. Some of the operational requirements are listed in this slide. The first one will be mission instruments must point at the target during the observation. This is very typical requirement. And the next one will be the antenna of the spacecraft must point toward the Earth during the observation time to keep the communication link with the spacecraft. I think this is also a very natural requirement. And moreover, the third one is, in order to generate enough power, the solar array paddles must point toward the sun. during the operation phase. So if these requirements need to be satisfied simultaneously, the component layer design is usually infeasible, impossible. This is because the geometry of the spacecraft, the sun, the Earth, and the target object tend to change from time to time. So in such a case, gimbaling mechanisms for solar array paddles and antennas may be a solution to that increase the degrees of freedom in the design phase. But it should be noted that the mass of the spacecraft will increase accordingly. So you need to carefully discuss what kind of solar cells will be used for your mission. So compared to Earth orbiting satellites, most deep space missions will not experience as many eclipse cycles. But if they do, they should have a battery with sufficient capacity to survive the eclipse. And even if there is no eclipse in the operation, a battery is generally needed to handle attitude control anomalies and or to support the attitude establishment phase immediately after the release from the launch vehicle. And moreover, if your mission will experience repeated eclipses, you will need to reduce the depth of discharge, or we call it DOD, to avoid battery degradation, which will result in the need for a large capacity battery. And for the design of a power control unit, or we call PCU, you need to select an appropriate component that corresponds to the scale of the spacecraft power generation capability. So if the spacecraft can generate or handle very large power, then we should use large PCUs to handle the large power. So it leads to the large mass for the spacecraft. And based on the design work up to this point, power budget analysis should be performed to determine the size of the solar cell or solar array paddles. First, we organize a power mode table. The power mode is a combination of components to be turned on or off. And the power mode table shows what kind of operation will be performed in what power mode. Then we will identify the most power critical conditions by taking into account the solar distance and the solar direction during the worst case scenario. Then the size and the necessity of the solar array paddles are determined so that a power balance can be established under the worst case condition. So personally, I do not know of many papers on the design of power supply system for micro or nano spacecraft, but here is a reference to a paper that describes the power budget analysis for EQUULEUS in detail. So please refer to this paper for your reference. So now the seventh step, the last step in the design flow. Here we will perform the structural and the thermal design. In the structural design process, conceptual design, such as the one in this mission idea contest, does not require a detailed structural analysis like FEM model analysis. At this stage, the size and weight of the onboard component is probably already listed. So you can just assume or estimate that the mass of the spacecraft structure is a certain percentage of the total weight of the onboard component. For conservative purposes, we should or we can assume that this percentage is about 40%. It is also for Procyon, the structure mass was about 40% of the total onboard components mass, and for EQUULEUS, that value was 30%. So I think 40% is some kind of conservative estimation. And it is also necessary to consider the layout of the components and to estimate the size of the spacecraft. So I think the size of the spacecraft is part of the constraint requirement in this mission idea contest. Then for thermal analysis and design, you can refer to general satellite design methodology. But what is peculiar to deep space missions, especially those missions without eclipses, is that the thermal design must satisfy the allowable temperature range in a state of complete thermal equilibrium, rather than in a transient state of repeated sunshine and eclipse. So I think this makes the thermal design of deep space missions very difficult. So these two papers are on the thermal design of EQUULEUS. So in these papers, you can learn an example of the design process in the thermal design and analysis for deep space mission. So so far, we have followed this design flow to explain the design process of the spacecraft. I hope you can now understand the characteristics of the design for deep space missions by this explanation. However, please note that the actual design flow does not proceed in series as shown in this figure. For example, in the middle of designing the communication subsystem, the size of the antenna becomes too large. Then we may have to go back to the mission objective to reduce the amount of data in the mission instrument. Also, we may reselect an object closer to the sun to relax the power budget feasibility. And through such iterations, the mission and spacecraft design will gradually become more sophisticated. So the reality is that we need to conduct lots of iterations before completing the spacecraft design. So I think the designing a deep space mission is very difficult, but very interesting process. At least this process is very interesting for me. So I hope you will work very hard to design the mission that you want to realize. So this is my message in my lecture today. So in this lecture, I talked about how to think about deep space missions and how to design a spacecraft by referring to examples of actual exploration missions using micro and nano satellites. And deep space missions are not completely different from Earth orbiting missions, as you find. And many of the design methods of Earth orbiting missions can be followed in the deep space mission. However, deep space missions have their own characteristics and difficulties, and I hope this lecture has helped you to understand them. So I would like to note one thing. The following topics are specific to deep space missions, such as trajectory design process, mission instrument and operation design, and propulsion system design, and the communication system design. These are very specific to deep space missions. And in my lecture, I just overviewed what to consider in designing these subsystems or performing these tasks. So I hope you will deepen your understanding by attending the other relevant lectures after this lecture. So this final slide is show the list of references mainly on Procyon and EQUULEUS. So you will be able to learn how University of Tokyo or JAXA has designed Procyon or EQUULEUS spacecraft so far. So we have some overview paper about Procyon and communication system design paper for Procyon, and also we have ADCS paper. And for EQUULEUS, we have overview paper here, and we have ADCS, power, and thermal papers like these. So this document will help you design to start your design work. And the other difference is deep space network specifications. So this concludes my lecture. So thank you very much, and I will be very happy to accept questions. Thank you.
Wow, thank you very much, Professor Funase. I'm very impressed by the level of detail in such a fantastic presentation. And the use of the examples as well, I think, made your message very clear. It was good to see actual practical examples in your presentation. And so we do have time for a Q&A now. Professor Funase, you can stop sharing your screen if you would like. And I would like to invite the audience to please type your questions in chat if you do have any questions for Professor Funase. I know there's a lot of content to take in, but we have had some questions coming up throughout your presentation, Professor. So I'll start perhaps with the one which was first in line, because this person's been waiting very patiently. And this is from Bonnie, who was actually asking a question about the order in which you list the mission styles and whether they are gauged, that order, according to the complexity in the design, or if there was some other reason you listed them in that particular order.
Okay.
Professor, yep, there we go.
Yeah, I will share my screen.
Thank you.
Okay, so you mean the order of mission styles?
Yes, it was very early.
This one? You mean this one from flyby mission to sample return mission?
Yes, correct, yes.
Yeah. So I think the top is most simple mission, and bottom is most complicated, and the large system is required. So flyby mission does not require much delta V, and just fly by the target without doing much trajectory control maneuver. So I think the flyby mission is the most simplest style when you conduct some deep space missions. Excuse me.
Yeah, I see. Okay, yeah. So the level of complexity does obviously increase with each of these. Yeah, okay. All right, understood. Thank you very much. The next question that we had was from Yasu, which was actually about your work with the EQUULEUS project. And they were asking, what are the scientific objectives in exploring the lunar Lagrangian point, and how will this help advance our future exploration?
Okay, so this is EQUULEUS mission, and the EQUULEUS is mainly the main purpose of EQUULEUS is technology demonstration, not scientific observation mission. And our technology demonstration mission is to demonstrate the very efficient trajectory control techniques around the Earth or Moon. So, for example, we are planning to. I have some backup charts. Can you see this slide? So, EQUULEUS will go to the lunar Lagrange point, and in order to do that, EQUULEUS will follow this very complicated trajectory, which uses lunar gravity assist many times. So by using this very efficient trajectory control techniques, we can do a deep space mission in the future by departing from the lunar base or lunar orbiting platform, which will be constructed by NASA and the international partners. So this very efficient orbital control techniques will pave the way for CubeSat to do a deep space mission such as astral exploration by starting from lunar orbital platform. So I think that the technology demonstration mission is the main point for this EQUULEUS mission. And also we utilize the flight environment from the Earth to lunar Lagrange point. We conduct some scientific observation within the mission period. We have Earth observation mission, Earth plasma observation mission, and dust impact observation mission for the lunar surface and so on. So we have engineering mission and such kind of science observation mission.
Excellent. Thank you, Professor. So that's something that our attendees, if you are planning on joining the competition, to keep that in mind, because your task is to design a mission, but it should be something which is innovative and novel and actually contributes to a deep space exploration. And so Professor Funase is indicating here that this is more of a demonstration of novel techniques rather than an observation mission or something which is seeking to obtain some specific scientific data. So that might be something you would like to consider when looking at your own mission design as a potential candidate for a mission design for yourself. The next question that we had was from Uriel, who asks, what are the further findings about the Earth's hydrogen corona? This was in regards to Procyon, and does it play a factor in creating or sustaining life on Earth?
Well, thank you for the question. So, Procyon observed the hydrogen atmosphere around the Earth by such kind of ultraviolet telescope, but I'm not so familiar with the science itself. So today I'm not able to answer your questions correctly. So I'm very sorry for that.
That's okay.
So, but we have some papers to in the geophysical research letters here, so you can refer to the paper for the
that's a good idea. There's some good resources there, I'm sure, that you can refer to, Oriel. Moving on to the next question. This is actually by Hong, who asked, how is radiation hardness for deep space missions different from Earth orbit missions, especially with CubeSats, which have a lot of commercially off-the-shelf hardware being used in them?
Yes, thank you for the question. So my personal opinion is that the radiation environment is not so different from Earth orbiting missions. So we typically design Earth orbiting CubeSat to withstand some kind of 10 kilorad or 20 kilorad radiation effect. And we And for Procyon mission or EQUULEUS mission, we will also impose the requirement of 10 or 20 kilorad radiation tolerance. So I do not think there are much difference between Earth orbiting mission and deep space mission. So in conclusion, I think you can use some the CubeSat components for Earth orbiting mission for your deep space mission.
I see. All right. Well, that perhaps will make it a little bit easier when selecting components. The next question we have is from Yasu, who has actually been very active in the chat with questions. And they ask, are there any examples of missions with spin-stabilized spacecraft that was specifically significant or meaningful? And Funase-sensei, if you could stop sharing your screen, that would be fantastic, because then we can all see you much more clearly. Thank you.
So could you repeat your questions? So your
Absolutely.
questions about the spin stabilization spacecraft?
Yeah, that's right. Yasu was asking if there's any examples of missions which are spin-stabilized spacecraft that was scientifically significant or meaningful.
Well, as far as I know, most of the deep space missions are 3-axis stabilization, but in some cases, such as magnetic field observation missions around the planet, and then we usually use spin stabilization spacecraft to rotate the spacecraft to measure the 3-axis component of the magnetic field. So it is very rare, but the case exists.
And are you able to, this is just from my own personal interest, are you able to expand a little bit on spin stabilization and the difference in terms of the engineering that goes into it at all?
Yeah, most difference between the spin spacecraft design and the 3-axis stabilization spacecraft design is that actual sensors and is totally different between them. So usually the gyro and star tracker is designed under the consumption that the angular rate is not so high. So this is because they are assuming a 3 stabilized spacecraft. But for spin stabilized spacecraft, it's spinning gradually. So maybe different types of actual sensors is required. So, and unfortunately, the CubeSat market does not deal with such spin sensors for spin satellites. So you must investigate the very old large components when you want to design a spin stabilized spacecraft for your mission.
I see. Yeah, that's very useful information for anyone who is potentially considering that. But yeah, obviously the 3-axis stabilization has superseded the spin stabilization too. Yeah, so just to keep that in mind for anybody who's looking at actually joining the competition. Our next question was actually from Yasu again, who asks, is the design flow for subsystems of the mission in the order of priority or criticality, i.e. communications, and is that order specific, the reason why you chose that?
Oh, let me share my screen.
Sure.
So, okay, well, sorry. Can you see my screen?
Yes, we can now, yes.
Yes, the question was the most critical process to influence the feasibility of the deep space mission, right?
For the subsystems, for the design flow, talking about the order of priority for the design flow.
Yes, so in my talk, I arranged, I made this flow in the order of importance or criticality to confirm the feasibility of the mission. So I think the top level is the most critical or in the feasibility of your mission. And so target selection and trajectory design strongly influence your mission feasibility. So this phase is most important phase.
Would you be spending more time on those earlier phases each time you go
yes,
through your iterations? Yeah.
Yes.
Okay.
Right.
All right.
Yeah, go ahead.
Oh, sorry. No. You go for it. I was about to move on, but if you've got more to add, I'd love to hear.
Yeah. So my talk today is very introductory, but and I did not deal with the very detail of the trajectory analysis. But yeah, if you want to reduce the delta V, so and make your mission feasible, you will need to consider some gravity assist techniques. But it's a very complicated process and need very expert skills. So so it would be very good if you will not use that kind of complicated techniques, and then you will your mission is feasible. So I recommend that not using such kind of very complicated calculation.
Right. So try and aim for a little bit more simplicity there.
Yeah.
And I did also post the link for pickup from ESA. You can actually follow that link in the chat, and that will take you to a website which you can actually go to the GitHub and download all the open source code for that program that Professor Funase was so graciously sharing with us. We do have one more question actually, and we've got a little bit of time remaining. So if anybody does have another question, we can probably sneak an extra in. But this one is from Uriel again, who asks, is it possible for a single micro nanosatellite to conduct multiple deep space missions with varying mission styles?
Oh, could you repeat the question?
Sure. Sorry. The question was asking if a micro or nano satellite is able to conduct multiple deep space missions that have varying mission styles. So example, from a flyby to a landing deep space mission.
So you mean you want to perform flyby mission and orbital mission at the same time?
Yeah, that's right. Or one then the other, and
okay.
able to move between the different mission styles.
By very small micro satellite. I don't think it's very easy since the launch capacity is very limited. So yes. If you leave from the but yes, my personal opinion is micro deep space mission by micro nano satellites should be very simple and should focus on one specific scientific topic. So I do not recommend to consider such kind of multiple styles of missions at the same time. So yeah, it's my opinion.
Yeah, I see. It seems like your complexity would increase exponentially, and you're also potentially increasing the amount of hazards or failures that you're introducing with that type of thing as well. So yeah, keep it simple is the message there. We did have a question from Taichi, who asks, or who says, the design flow seems very general. It's not limited to nano micro satellites. Usually at which point do you need to make your decision on what type of mission you want to design? In other words, how can we judge if the mission concept we have fits in the frame of a nano or micro satellite?
Thank you for the question. So as I explained in the talk, target selection and trajectory design roughly determine the feasibility of the mission within the launchable mass. So if we perform target selection and trajectory design, then we can judge if this mission is performed within the micro or nano satellite. So yeah, at this step, we can judge what kind of mission is possible or impossible.
I see. Okay, thank you very much, Professor. And we've had another question from Angelo, who asks, will it be demanding for the power and thermal systems if the spacecraft uses RTGs instead of solar cells?
Will it be demanding for the part? Yes. Yeah, actually, RTGs will simplify the design, the spacecraft system, because it does not require any gimbaling mechanism or for solar panels and so on. But yes, as pointed out, yes, the RTGs will impose some difficulties regarding the radiation hardness of the components and the thermal design, or the handling of the thermal dissipated thermal energy. So I think for very small spacecraft, solar array panels or solar cells will be better in the use of in the design.
I see. So with RTGs, radioisotope thermoelectric generators, for those who don't know, what about the difficulty in actually putting them on a satellite, which is you know, a smaller structure or a limited mass, and then also too I suppose the public perception of using that type of power source for these types of projects?
Yes, it has at least some political difficulties, at least in Japan, and also in the world. But other than this aspect, yeah, the RTGs always emit radiation throughout the mission phases. So usually RTGs is mounted on the tip of the long boom to avoid the radiation from the RTGs to the spacecraft itself. So I think it is very difficult for very small spacecraft to have RTGs within very small envelopes. So it is one of the difficulties in using RTGs for small spacecraft.
I see, yes, that makes sense. Now, I'd like to just ask if we have any other questions from the audience. You have your opportunity now. If you've got anything else you'd like to ask Professor Funase, please do so. I'll just let you all know as well that the recordings and the lecture materials, including Professor Funase's presentation, will be made available on the website after the session today. And you can find all of the requirements and criteria for MIC7 on the MIC7 website. And so if there's no further questions, please join me in thanking Professor Funase for providing such an incredible and fantastic lecture, which has really, I think, sparked our curiosity. And we've had some good conversations and good questions out of it. Thank you very much, Professor Funase. And if there's anything you'd like to add or any closing statement, please do so. Thank you very much.
Yeah, thank you very much for attending today's lecture. So I was not expecting so many attendees, so I was very happy to talk with you.
Professor Funase, thank you very much once again. And just before you go as well, I'd like to quickly just share my screen with you all, just to give you a little bit of a reminder of some of the important dates for the MIC7 contest. So here on this screen, this talks about the rationale behind MIC7 and the opportunity which is given to you to actually be, if you're interested in deep space, you can actually explore the opportunities that are there for missions and present your ideas. You can actually gain attention internationally as well through this opportunity. The important dates are listed here. And the first one is the 7th of July, which is the submission date for your abstract. It's when it's due. We will be opening up the registration site closer to the date, and you will need to submit your abstract with your registration. And then after that, we will provide a notification to those who are moving through to the next round on the 18th of August, with the full paper submission due on the 30th of September and the final presentation to be decided yet, but it'll be sometime in November. So here we have just the little flow that we just went through before. The presentation for the final session in November may be done in person or online, depending on the conditions at the time, and we'll notify you closer to that date as to what the presentation will be. And our next lecture in the series is Professor Ueno, who will be presenting on science operations of space missions this Thursday, same time, and we'll send out an email to remind you all of that as well. So just very quickly to remind you as well, or if you're thinking of reasons why you may want to join MIC7, these are some of the reasons. You can build capacity and you can actually seek meaningful mission ideas. We do have these free lectures that you can attend. Some of these projects that have been part of the Mission Idea Contest actually result in missions which are innovative, affordable, and actually reachable. But you will receive some type of exposure for your idea if you're successful, which can help you develop your career profile. And we do have awards and prizes, which we will announce closer to the dates of the competition as we move forward. So please join us if you haven't already downloaded the abstract template. Please do so. This is the link that you can download the template, and we'll notify you when we open up the registration site for you to submit your abstract. But thank you very much for attending today, and we hope you enjoyed the lecture, and we hope to see you again on Thursday for Professor Ueno. And once again, we would like to thank our honoured guest, Professor Funase, for his valuable time and contribution. You have enriched everybody's ideas here, I'm sure. Thank you very much, and we will see you hopefully on Thursday.